population is about another logistic which has extra term. It's called harvesting term in there. This is particularly for the fish model. So we look at the logistic and then minus the H, which is the harvesting factor that would affect to the population rate. So the population is harvested. That's why it has a minus sign as a general explanation for this logistic equation involving harvesting. So for our case, the model is in the form of dPdt equals P times 3 minus P minus 9 over 4, where the initial population is P subscript 0. P subscript 0 as understood to be the non-negative number. We can use it to find the analytical solution later in part B and part C. Again, this equation is still autonomous. So part A asks you to use the phase portrait concept to sketch the solution curve. And then in part B, we're gonna solve. Solve means you use appropriate technique, separable, linear, whatever that works that you think is appropriate for this problem. And then part C, use information in part A and B to determine whether the fishery population becomes extinct in finite time. That means, would that be possible that the population goes to 0? So P equals 0 in finite time. That means, can you find that time? Can you tell exactly what is that time? If you can tell, what would that be? So we're gonna do a little bit more algebra work after we get the solution in part B, as we are finding the solution for part C. And the solution I put on the end here. So that's what we aim to get. All right, so for the population model, we see dPdt. Let's start with part A. dPdt equals P times 3 minus P minus 9 over 4. As you see, the right-hand side, they all like either in P or the numbers, nothing involving T, another autonomous form. To sketch the phase portrait, same way as what we did before. We look at the vertical line and then locate the critical number. The critical number occurs when dPdt, or the rate of the population, equals 0. Therefore, we are going to solve P times 3 minus P minus 9 over 4 equals 0 and see what are the number P. Make it the rate of change to be 0. Okay. It looks like not simple as the logistic model in general. What you have to do is just like expand them all out and readjust the term. Okay. For this case, we have like 3p minus p squared minus 9 over 4 equals 0. My suggestion when you deal with the when you deal with the fraction form, try to avoid getting into the complication. Multiply all by 4 and you will not lose anything. Just make the problem less complicated. For this case, if I multiply all by 4, I will get 12 times p minus 4 p squared minus 9 equals 0. And then I just rearrange the term with the negative side here and 4 p squared minus 12 p minus now become plus, the middle term is negative side, the last term become plus side, plus 9 equals 0. And with this way, we can see that this is the perfect square, or you can factor, like it's going to be 2 times p, and this will be 3 and 3 minus sine equals 0. Or we can see this is negative of the 2p minus 3 to the power second equals 0. Okay. Now we have the critical number p equals 3 over 2. Just one critical number. And then draw the phase portrait as a vertical line, or actually that's the axis of the dependent variable. In this case is the p. Locate the p equals 3 over 2 on the line, And this is the population model. We're gonna bound this one at 0, at p equals 0, because we don't want to do anything when p is less than 0, or it doesn't make sense, or it's not applicable. So for the critical number p equals 3/2, we're gonna check out whether the dp/dt, or the rate of change for each interval, the sign positive or negative. Okay, the reason that I keep everything on one side and take the negative sign out, because I want to maintain the same form as the original expression on the right hand side of the dp/dt. So when I check the sign, plus minus sign of dp/dt, I'm going to check from dp/dt equals negative. Actually, I factor the 4 out, right? I multiply by 4. Actually, this is the same as 1/4 times 2p minus 3 to the second power. Because you see the number 4 here, I adjust it because I want to make it as non-fraction term. And when you go back to original dp/dt, that would be negative 1/4 in front of the quantity square. You can recheck it by multiply it back or expand them all out. It should get back to the original term, which is p times 3 minus p minus 9/4. So with this original form, and we know that 3/2 is the critical number, pick the number same way as what we did before. Any number that greater than 3/2. For example, if p is 2, okay, 2, when you replace p with a 2, so the quantity there becomes positive sign. Actually, the power 2 here force everything in the parentheses here to be positive no matter what. But after that, we multiply by negative 1/4. The sign gonna be negative. The sign gonna be negative. So that's, I should not put the arrow up there. So that means for the interval p greater than 3/2, the rate of change is negative. So the arrow coming down. And then gonna be the same situation for p between 0 and 3/2, because the power 2 here make the quantity to be positive after you multiply itself. And then multiply by negative 1/4, still the derivative gonna be negative for another interval. And now we can see the p equals 3/2. This is not stable, this is not unstable, but this is a semi-stable. Okay, p equals 3/2 is semi-stable. You guys okay with this so far? Yeah. All right. If this is the semi-stable, now if we sketch the graph or the solution curve, so this one is a phase portrait. And then for the solution curve, like the slope field, so you have the arrow down for both regions. So any initial point, any initial population, if you keep going, the solution approaching to this line, anything below is gonna go away from that line and keep going. But the cutoff at p equals 0, if we don't locate the p equals 0, the graph is coming down furthermore. And from the phase portrait, that you can see that at one point the graph gonna go across the horizontal axis, or it's gonna happen when p equals 0. So some point of time here that we're gonna find in part C. Okay,